Hi guys, and welcome to Codeforces Div 2 round number 788. As you can see, contest has finished and system tests have already completed. I couldn't solve all problems in contest even though I tried quite hard. Got TLE on some of the pre-tests because I missed some small idea which I then fixed, and as soon as system tests got over, I could submit and it worked. So, unfortunate to not get last problem, but still quite a good performance to get first 5 problems. So let's go over the problems. In problem A, we had an array of non-zero elements. We wanted to sort it. For that matter, we were allowed to take two elements of different signs and swap their signs. So negative becomes positive and positive becomes negative. So what I noticed, there is an invariant in this problem that number of negative elements does not change. So, and also clearly all negative elements should precede all positive elements. So let's do just that, count number of negative elements. Let's say that we make prefix of elements negative, suffix positive, and then just check if it's sorted. Because this is the best that we can do. Right? Because all negative elements should precede all positive. And number of negative elements is fixed. So that's it. In problem B, we had a string. String contained certain special characters, and we were allowed to perform the following operation. For each special character in the string, remove the previous character, and this happened simultaneously. We wanted to know what is the maximum number of operations that we can perform. So in this problem, I noticed that you can partition string into blocks of special and non-special characters. And the number of operations is roughly the length of the maximum block of continuous non-special characters. So this is what I do. I go over all characters, maintain the length of the current block, and sometimes length is length of current block plus 1, sometimes length is length of the current block. Specifically, once you can see that when you perform an operation, the length of each block of non-special characters decreases by 1. So after you performed maximum length of block of non-special characters operations, you don't have non-special characters, and the maximum number of operations, well, except for potentially some suffix. And now the only time when you can perform an operation is when you have several special characters next to each other, which may have resulted from one of the blocks of non-special characters disappearing. Then two neighboring blocks of special characters, they merge together. And this happens for every block of special characters except for the first. So if the current block is first block of special characters, then answer is current block of non-special characters. Otherwise, it's current block plus last special character of the previous block. And that's it. Partitioning string into blocks is a good common idea. In problem C, we had two permutations. We wanted to construct a new permutation from them by maintaining indexing, but like for each index I, either taking AI or BI. We were given a partial information about permutation C, like we know some elements and some elements are 0. We wanted to count the number of potential permutations C. So for this I noticed, let's actually take a look here. So it's well known that permutations decompose into cycles. And what we will do is we will decompose these permutations into cycles in such a way that each cycle will come either completely from B or completely from A. Let's see. Let's take a look at the first index here in the last sample. If we take element from B, that is number 3, then in the last index or wherever 3 appears in the first array, it cannot be chosen. So we will also have to take 2 from the second array. Then wherever 2 occurs in the first array, we will also need to pick the corresponding B element. So you can clearly see that how decomposition should work. You compute inverse permutation of A, and then you follow B and inverse of A. Inverse of A answers the question where in A is on which position in A is a given element. So this permutation inverse of A times B gives you decomposition into cycles, and for each cycle it may have fixed value. It is fixed if it is not does not completely consist of zeros or negative ones after I subtract it. But also there is one tricky moment. If this cycle, in this cycle, A is completely equal to B, then even if permutation is not fixed, you still don't get a choice. So there are two properties that are important for each cycle: whether the value A or B is fixed, and whether picking A or B actually makes any difference, so whether the value is unique. If the value is not fixed, not unique, then number of ways you can pick this cycle completely either from A or completely either from B. So that multiplies answer by 2. And this could have been noticed very easily from samples, that answer is always a power of 2, so that is a big hint towards like decomposition into some pieces that can be completely taken from A or completely from B. So that's it for problem C. In problem D, we had hexagonal grid and we wanted to draw some lines in it, and they created such triangles. We wanted to draw minimum number of lines to create given number of triangles. So here I kind of assumed that number of triangles, let's say that there are A horizontal lines, B lines with positive slope, and C lines with negative slope. So I group lines by their orientation or angles that they form with x-axis. Then you can see after some experiments, particularly after looking closely at these two cases, you can see that if you have A lines in first orientation, B lines in second orientation, and C lines in third orientation, the number of triangles that they form is bounded from above by this value. It is not hard to show that if we want to maximize this quantity, then A, B, and C should be roughly equal. In particular, they should be roughly their sum over 3. So that's what I do. I do binary search over the sum, and then each of them starts with roughly quotient, and some of them may be greater. So if I have any remainder, then I first give it to A, then if there is still something remaining, I give it to B. And this condition is never true, but I decided to keep it for uniformity. So yeah, then I just check if I constructed enough triangles. If I haven't, then I need to increase my lower bound. Otherwise, I can decrease my upper bound. So yeah, this is problem D for you. And to get that many triangles, you have to draw lines with step of 2, I believe. So like, don't draw a line through the center of adjacent hexagons, step aside a bit further, and you will get the necessary number of triangles. Problem E is a cute constructive problem where we have a tree. We want to write some value in each vertex and on each edge in such, and also we want to root a tree in some way to minimize the following number. For each pass that starts at root and goes down, we compute its XOR. So let's say 1 XOR possible is 3, then 3 XOR 7, 3 XOR 7, XOR 6, etc. All of these paths should be... We take XOR of each such path, we take maximum XOR, and we want to minimize maximum XOR. So here I immediately noticed, because of special constraints, that number of vertices is a power of 2, that there is an obvious lower bound on the answer, that is 2 to the power of p is the lower bound on the answer. Because if you consider most significant bit, and first time it occurs on any pass, the prefix XOR will be at least that much. Then I realized, okay, well, maybe this lower bound is achievable because it was the case in samples. So I decided, okay, how can I achieve it? Let's say I write 2 to the power of, let me actually open my submission. Let's say I write n into root, and then for each, let's say I run DFS. For each vertex, there is a except root. For each vertex except root, there is a corresponding edge that connects this vertex with its parent. So it kind of made sense to make those two differ by 2 to the power of p, to cancel out the remaining label. And then depending on the layer, even or odd, you had to either assign to odd edge bigger label and to vertex smaller, or to edge smaller label and to vertex bigger. So your main idea here is that a pair of vertex and the edge that you visited directly before visiting this vertex, their XOR is 2 to the power of p, so most significant bit. And this order changes to ensure that partial pass that ends at edge, because such paths were allowed by the problem. So this if-else switch is necessary to ensure that partial pass that ends in the middle of the edge also does not have a big XOR. But other than that, each edge vertex pair XORs most significant bit. So it's either get 0 or just 2 to the power of p, which is acceptable answer for us. And that was this problem. I think it's a very cute constructive. Obviously people are going to complain because it's constructive forces, but whatever. In problem F, we had to count the number of arrays A of length n such that their sum is in some range and their XOR is fixed. Array was reasonably short, but other constraints were not short. So what I did in this problem, after we scroll at coder mod int implementation, so first of all, you should notice that it's kind of hard to count directly arrays with sum in range. So let's just count arrays with sum less than or equal to given value. Then your answer can be expressed as a difference. So you take all arrays with sum at most r and subtract arrays with sum less than l. And you get your necessary arrays. Now how to count arrays with sum less than or equal to something? Well, we can use dynamic programming. It was kind of obvious that you need to do dynamic programming over bits, but second parameter in contest I got wrong. Luckily, I was able to fix it shortly afterwards. So what we do is the second parameter will be margin. That is how much smaller than r we currently are. And the point is that margin is limited from above, because if our margin gets too big, then it's already guaranteed that we will never exceed value of R. You may think about it as because we consider bits from most significant to least significant, it follows that if your first bits were too small, then no matter what you put into the remaining bits, it will still be too small, so there is no point in distinguishing just how small your first bits are if they are too small. So that is first thing. Notice that we will have margin. Is how much margin denotes how much smaller our prefix is, prefix of bits, than the prefix of R. Now, once we fixed some margin, when we consider next bit, like all previous bits are twice as significant now. And also, if R has current bit set on, then our margin also increases. Once we have margin, we can loop over how many numbers in the current bit turned on. So obviously this number should have the same parity as corresponding bit in Z. That is XOR of all numbers in the array. So it clearly defines parity of, like, if Z has current bit turned on, then odd number of array elements have this element on. If Z has current bit turned off, then even number of array elements have this bit turned on. So we loop with step of 2. Clearly we cannot exceed n, but also we cannot exceed margin, because if we exceed margin, that it means that we already took too much, so our sum is too big. So that is first optimization, that we never exceed the margin. Second optimization is that technically our margin becomes new margin minus k, how much of a margin we just used. But if it's at least n, then we kind of don't care, because the number is already too small. Even if we put all the bits and all the numbers, because the next bits are less significant than our current prefix, it doesn't matter. Like, we are already too small, so we group all numbers that are too small together. Now, how to do the transition? Well, we just said that we, out of n array elements, we want k of them to have current bit turned on. There are obviously binomial coefficient of n by k ways to choose the corresponding k elements to have current bit turned on. So that's a multiplier in your transition. And then we just sum up the resulting array. So yeah. This allows us to compute the number of arrays that have sum less than or equal to r, and then we subtract. Binomial coefficients you can compute with dynamic programming. You can also compute them with like pre-compute factorials and inverse factorials. Then you can compute binomial coefficient in O of one time. But obviously, pre-compute binomial coefficients is even faster than that. The difference is constant term, which didn't matter in this problem because we are too fast. But because I was optimizing somewhat less efficient DP, I decided to go with race here. So yeah, thanks everyone for watching. I hope you learned something new, and I'll see you tomorrow with an editorial for AdCoder Grand Contest. Yes, we have AdCoder Grand Contest, which is very cool. See ya. Bye bye.